Stanford University.
How many of you think that CCS is a good idea? Raise your hand if you think it's a good idea. Okay, well, pretty friendly audience. How many think that CCS is a bad idea? It's okay to think it is. Okay, there's 1, there's 2, there's 3, 4. Okay, yeah, it's fine. That's totally fine. This is not. I'm not an idea police. So it's really important that we recognize the diversity of opinions, because there aren't easy answers to the challenges. And I think that I personally enjoyed both, actually all 3 of the talks this morning, the Chinese perspective and the US perspective, that on one hand, this is a tremendous challenge to deal with these issues, but I think we heard optimism on the part of our officials that in fact there is a path forward. And I personally think that CCS is one important component of that, but clearly just one component. So carbon capture, so CCS, so that's sort of the shorthand that we use when we talk about carbon capture. You'll notice that it also has some other names like carbon capture and geological storage, so that's CCGS. Sometimes you'll hear CCUS, that's carbon capture and underground storage. Sometimes you'll hear the word storage, carbon storage, and sometimes you'll hear the word sequestration. So all of these things for people who work on subsurface injection of CO2, that's all the same words. So since you all are such experts, maybe you don't know a little bit about the history of why we say storage versus sequestration. So as the international community got together, in the UK, people called it carbon capture and disposal. But that sort of had a bad connotation because disposal is what you do to a waste. And if you're in the EOR industry, CO2 is an incredibly valuable commodity, so you don't want to dispose of it. That gave the wrong connotation. In the US, we called it sequestration, which I think I've got a definition for sequestration. It means is the state of being alone or to keep apart from others. So basically the idea that you isolate CO2 from the environment. That's sort of how we think of the word sequestration. So there was a big movement in the US to call it sequestration, but then we got together with the Europeans, particularly and Northern Europeans, and sequestration in Northern Europe, and also I guess in Spain, means a bad word. It means like to kidnap, so it had this really negative connotation. So somehow in all of those machinations, people now mostly call it carbon capture and storage. I don't. I usually call it capture and sequestration because I think storage is a little bit misleading because it's like you're going to store it and use it later. And the reality is that we have so much CO2 that it's hard to imagine that we're going to be using that much of it later. Certainly some might be used for EOR. So I prefer to say sequestration, making it clear that we're really setting it aside. Because some people might think that if you use the word storage, that it's sort of misleading, that it tells people, oh, well, we intend to get it back. And in reality, we don't. So there's a lot of concern about being open and honest with the public. And so some people don't like the word storage. So anyway, that's what we're going to be talking about is CCS. And basically, CCS is a 4-step process. So if you go back to this picture here, whoops, we have a power plant. We're burning coal or we're burning natural gas. We are combusting it in air. And so we have a smokestack that's got a mixture of nitrogen and carbon dioxide. If it's a coal plant, it's about 15% CO2 in the effluent coming out. If it's a natural gas plant, it could be half that or less. And if it's an industrial process, maybe it's about 5%, and the rest is nitrogen. So that creates a big problem because one issue, maybe we can talk about this for a minute. So one possible idea is you would just sequester all of the CO2 or all of the gases coming out of a power plant, right? Why not do that? Then we don't have to separate it. But the problem is that would take an enormous volume of the underground space. And whereas people believe there's a lot of room underground, if you had to store all of that nitrogen in addition to the CO2, it would be impractical. So that leads to the first step of this four-step project, and that's something we call capture. It's sometimes also called separation, and basically the goal is to extract the carbon dioxide from the gases that are coming out of a combustion source. So that's step number one. So now you have CO2 gas, okay, at fairly low pressure. And the next thing is if you want to move it around, if you want to transport it somewhere, it's very inefficient to transport a gas because the density is low, so you have very high velocities or you have very large volume that you need to move around. It's also very compressible, so it's quite inefficient to do that. So the next step is to compress the carbon dioxide into a liquid, basically. So if you compress it enough at room temperature, if you go to 100 bars or so, CO2 is actually a liquid. And whereas it's a little bit different from water, for example, it's less viscous, the density is actually about the same as water. So you can think now the second step is compressing the CO2 to this liquid that's pretty much like water. So the next thing is that you now have this quantity of CO2, or this steady stream of CO2 liquid, and you want to figure out where to put it, but you need to be able to transport it. So the next step is to put it in pipelines, just like natural gas pipelines, or there are also oil pipelines or water pipelines, but you need to put it in a pipeline for transporting it to someplace. And then the final step is to inject it underground for geological sequestration. So that's sort of illustrated here by this very schematic picture. So we no longer have CO2 coming out of the stacks. We've got nitrogen and water vapor. And we've taken the carbon dioxide, we've compressed it, run it through a pipeline, and injected it deep underground. Now this is a kind of deceptive picture because if you notice the scale here, this is 1 kilometer, this is 2 kilometers, so this is about a mile deep. So when we talk about putting CO2 underground, we're talking about putting it, just sort of, I don't know, if your metric system, think about a kilometer. If you like English system, think about a mile down. So we're talking about it, putting it very deep in the subsurface. So that's the basic way that this technology works. So what I want you to do now is that you all got little booklets, and actually gave you those so that you could write down notes as we go along. And I want you to do one thing. I want you to write down 3 questions or 3 issues that you have sort of the most questions about CCS. And then I'm going to ask you to speak to your, say, 2 nearest neighbors and compare notes. And then I'm going to ask a number of different groups what you think the key issues are. Because I want to make sure that we actually talk about those as we go along. Okay, so we will have like, I don't know, 3 minutes or so to, well, how about 5 minutes? 5 minutes to write down your 3 questions and talk to your neighbors, and then we'll do a little report out. But carbon capture and storage, you really do it because you're trying to reduce the CO2 emissions. And you guys all know this, that the Industrial Revolution was built on the back of fossil fuels. These are very energy-dense resources. Our engineers were brilliant to design combustion schemes that allowed us to use this energy, and consequently we built this whole society that we have today. But as a consequence of this, we released a lot of carbon dioxide into the atmosphere. And the challenge is that when you put carbon dioxide into the atmosphere, it stays there. So this graph, I like this one. This is a 10,000 year period. So this was 10,000 years ago, and this is now. And for a long time, the CO2 concentration was nearly constant. And then beginning with this Industrial Revolution, when we started to burn all these fossil fuels, we see a dramatic increase in the CO2 concentration in the atmosphere. And CO2 isn't like other pollution, like particulate pollution, where if it rains, the particulates come out of the air. When we put CO2 in the atmosphere, it's there for hundreds of years or longer. So we put it up there, it stays. The consequences, of course, we know lots about global warming. And even today, if you look at the fires in Russia, if you look at the floods in Pakistan, these are all the kind of effects of extreme weather events that are anticipated by the models. So climate change isn't something in the future. Climate change is something here today. And we need to reduce emissions to address this. But the other thing is that it's often talked about a lot less because the global warming issue is so large. But by putting CO2 into the atmosphere, we acidify the surface of the ocean. And many of the organisms that live in the surface of the ocean build their shells out of things like calcium carbonate. And when the water is slightly more acidic, they have a very hard time reproducing so successfully. And those organisms are at the base of the food chain. So the main drivers of why we need to consider CCS are to stop emitting so much carbon dioxide into the atmosphere. And we need to begin to do it now. And we need to reduce it a lot. So there's an urgency to addressing these issues. So one could say, well, fine, we have to stop emitting carbon dioxide into the atmosphere, so why not just stop burning fossil fuels? Well, if you look at our energy system today, 85% of the energy that we use comes from fossil fuels. So basically, the majority of our energy system is built on this. This is what we know how to do really, really well. And in spite of all of the, I think, optimistic discussions we heard this morning about the rapidity at which we could reduce emissions, if you look at other estimates by, for example, the IEA, they suggest that by 2030 or so, that still 80% of our energy will come from fossil fuels. So there's just a lot of built up momentum. There's a lot of infrastructure that's been built. So whereas there's lots of opportunity with solar and wind, and as you participate in the GCEP conference, you're going to see a lot of fabulous work on solar PV. You're going to see work on biofuels, on hydrogen, all very, very exciting things that we have a lot of enthusiasm for and optimism about. But nevertheless, at least it's my personal view that we're not going to be able to solve the CO2 problem unless we sort of work head-on to reduce emissions from the combustion of fossil fuels. So the other thing is that, well, maybe we have peak oil and that we're going to run out of oil anyway. There's some views about that, and that we'll basically have to make this transition. But in fact, there are many assessments about the availability of fossil fuels that suggest that, in fact, that there are lots of fossil fuels still remaining. And this is a chart that we prepared at GCEP that basically looks at the ratio of the size of these resources compared to the amount of energy we use every year today. Okay? So this number 1 corresponds to what do we use today. So if we had 10 times more of the resource left than we have today, it would be here, 100 times more, 1,000, and so forth. And if you look at coal, if you look at gas hydrates, these are gas and ice, basically an ice encased gas hydrates. If you look at oil, if you look at gas, all of these resources are very large. And in fact, information continues to change on the availability of those resources. The x-axis. These here are these different, so this is geothermal energy, so this is the total amount of geothermal resource. So it's the resource, it's not a reserve, it's a resource. So it's the maximum theoretical amount that's available to be measured in. These are measured, okay, so these are in the units of, I took off the units. These are in exajoules. No, that's wrong. These are just the multiplier. So for example, it's just 10 times. So we use 500 exajoules of energy every year. So this corresponds to 500 exajoules. This would be 10 times that, and this would be 10 times that. So it's all divided by what we use today. Yeah. So this is the size of the resource divided. So the simple way to say that is to say if we could use all of this, that we have enough natural gas for 100 years worth of supplying the total energy demand. Now that's a too simplistic way to look at it, but that's basically what this means. So this says that for coal, we have 400 or 500 years worth of energy stored in coal that could conceivably be used by us. Yes?
Do you have any idea where like solar and wind are on that?
Yeah, so I do have another chart, which I'm not showing here. So the solar resource is absolutely enormous. It's about 8,600 times the amount of energy that we use on an instantaneous basis. Wind is about 600 times. And those are the two big renewable resources that are available. Biomass and so forth are more like 5 to 6 times. Yeah.
Still much less than like geothermal.
Well, so they're not directly comparable because a renewable resource means you use this much today, but the same amount is available tomorrow and again and again. So these are depletable resources. So if I use if I use half of this gas, well, then I've only got half left. Whereas if I harvest the photons from the sun one day, well, the same amount is still there the next day.
So the simple question is to harvest it, to be able to harvest it realistically.
Right, yeah, so these are the theoretical maximums, and the reason that we look at this way is we're in the business of providing new technology solutions. As long as the first law of thermodynamics and the second law of thermodynamics are not violated, these are potential, resources that we can harvest. Back there.
I was under the impression that methane clathrates were kind of off the scale in terms of the resource stock. Mm-hmm. Is that considered in the hydrates?
Yes. Mm-hmm. Yep. These are, the hydrate numbers move around a lot, but these are the latest hydrate numbers by the USGS. Yeah. Okay. All right. So anyway, so the point is that we're not going to run out of oil and gas. But I guess I'll make another point briefly, is that a lot of these resources, though, are getting more and more difficult to get at. So, for example, if you have light, sweet crude oil, it takes less energy to extract that than, for example, the oil sands in Canada. It takes a lot of energy, which means you have a lot of CO2 emissions if you're harvesting some of these lower grade hydrocarbon resources. And similarly with coal, as the coal gets deeper and deeper, it gets in thinner and thinner seams, you have to use more and more energy, which translates to more and more emissions. So not only is it that we're not running out of these, but as we continue to tap them, the associated emissions are going to grow. So it's all the more reason, if we are going to use them, to find a way to reduce the emissions. Okay, so another argument for CCS is that it's many of the emission sources are amenable to this. So an estimated 60% of all of the emissions are associated with stationary sources. So stationary sources are things like power plants or cement manufacturing plants or steel manufacturing plants. And so this technology is applicable to a lot of the emissions on our energy system. And in fact, there are over 7,000 sources where the amount of CO2 coming out of the stack is sufficiently large to make it seem realistic you could apply this technology. And so this is just counting. You can see this is the number of coal-fired electric plants, gas-fired electric plants, and oil-fired plants, and so forth. So there are many sources to which this technology can be applied. However, there's a finite number. There aren't hundreds of thousands of these. There are thousands of these. So if you think about using CCS, well, one can imagine if you had several thousand CCS plants or plants with CCS, that you could reduce emissions from a significant fraction of these sources. Yes?
Is that just the number in the U.S. or worldwide?
That's worldwide. Yep. Yep. Worldwide as of 2005. So just one more slide on sort of the case for CCS. So Pam Matson, in her remarks today, talked about a lot of modeling tools that people use to try to understand our overall energy system, and one of them was these integrated assessment tools. And there are a number of these studies that have looked at how could we achieve emissions reductions of what we saw, 83% was the Obama administration target. There are other studies with 50% and so forth. And so people do these studies to figure out, well, how much emission reduction could we get associated with efficiency? How much could we get from switching to nuclear power? How much could we get from renewable energy? And invariably, when these studies are done, that the conclusions seem to be that about 20% of the emissions reduction, so this is an IEA scenario, for 50% reduction in CO2 emissions by 2050. And these top two slices are CCS. So one is CCS from industry, and one is CCS from electricity generation. So the first thing you see is clearly this is not the whole solution. However, it is sort of a 20% piece of the solution. And it turns out that industrial emissions in particular, after you've gotten, I teach a class where the students actually learn how to do this. And at the end of the day, if nothing else, the industrial emissions are very difficult to eliminate without CCS. And most simulations also suggest that the electricity sector is very, very difficult to decarbonize without CCS. So I like to think of it sort of as a 20% solution. Okay, so that was the why. So I hope I answered the question that somebody had about why are we doing this. It's basically to get rid of the CO2. Yes?
That 20% is now agreed upon in the industry of this?
Yes, it's generally, I mean, there are certainly people who disagree, who say we should use no CCS. There are people who might want to have more CCS, but the majority of these kind of tools come up with a 20% kind of number.
So including all the effort using solar energy, wind power.
Right, yeah. So actually, if we quickly go back to this scenario, this was basically end-use energy efficiency. This was generating electricity more efficiently. And let's look at the renewable wedge. That's number 4. So in this scenario, this is the renewable wedge. So you can see that the renewables is larger in this scenario than the sum of these two bars, but not so much different.
Is there a substitution of natural gas for coal in those numbers?
Yes, some. Though I think we're seeing, I mean, certainly in the U.S., there's a new perception about the availability of gas. These calculations were made sort of before the potentially larger source of natural gas was available.
Sorry, at the risk of being redundant, is scientific community or countries, agreeing this 20% is?
Well, so people agree that this is a reasonable global number. The global number. That doesn't mean every country would do this, because some countries will do none of this, and some countries, like in the Middle East, they might use this a lot. They've got a lot of place to put the CO2. They can use it for EOR and so forth. So every country shouldn't think, oh, I'm going to do my 20%. That would be the wrong approach to take. Yeah. Okay, yeah.
So is artificial photosynthesis considered in this analysis, such as CO2 to methanol?
Mm-hmm. That would come up in the renewables. Basically, it would be a solar conversion technology. I don't know of anybody who includes that level of detail in these assessments. However, if you notice, in this scenario, this continues to grow, and it's in part because of technological learning and the development of new technologies, lowering the price, increasing the efficiency, and that would be one example. If we get to the point in this time frame where that's possible, that would be an example of a technology innovation that's not explicitly accounted for, but nevertheless is in some general sense anticipated.
So that technology might overlap with CCS contribution in the future. Is that going to be important factor to affect the analysis here?
Yeah, you know, I think that when we look at artificial photosynthesis, at least the way I see it, its probably biggest opportunity is in transportation fuels. Now, that could be wrong. That could be a wrong assumption. Mostly CCS is applicable to the electricity sector and the industrial sector. So only to the extent that there's overlap between electrification of vehicles and Oh, I see what you're saying. Yeah, actually, I think that that's a really interesting opportunity to capture the CO2, and instead of injecting it underground, basically, you know, disposing of it, to reuse CO2. And in the electrofuels, maybe you weren't here this morning, you know, one of the things we're interested in is electrofuels, where you could use the CO2 captured from a power plant as a carbon source to make things like methanol or other hydrocarbons that could be used in the transportation sector. Yeah, no, absolutely. And actually, that there are many scenarios, this is a little bit of a diversion, but that now it appears that if we would hope to achieve stabilization of atmospheric CO2 at about 450 parts per million, that's what you would need if you wanted to limit the temperature change to an average of 2 degrees C increase. That the only way that you could accomplish that is if you have negative emissions, meaning that your global emissions aren't even zero, but you have to have, you have to basically be extracting CO2 from the atmosphere. So one possibility is to use biomass, basically biomass, burn it to generate electricity, or gasify it to generate electricity, and then take the CO2 and inject it underground. So it's actually a way of extracting CO2 from the air and sequestering it, and that would give you negative emissions. Most of the integrated assessment models looking out to 2100 suggest that we need a significant amount of that if we want to stay below 2 degrees C temperature increase. So, okay, so that's that. Okay, so that's why that there is such interest in CO2 capture and storage. So now what I'll do is I'll give a technology. Well, let's just quickly check on the questions. Okay, I think the only question that I really answered so far is why do we do it at all? So I think we've got a long list of questions, but we will get on to those. Okay, so first I'd like to talk about capture. How do we take carbon dioxide out of the gas that's coming out of a power plant? What kind of technologies are available? And there are basically 3 different technologies that are available today that have been used in other kinds of industries, in many cases on a fairly routine basis. So the first one is called post-combustion capture. So it means you go ahead and you combust the fossil fuel just like you always did, and then you have a smokestack, and then you try to capture the CO2 coming out of that. So here's a little schematic that we've got fuel. This could be natural gas. This could be coal. You have air. You basically burn this. You heat up water, and you run a steam cycle. And if you look at the gases coming off from combustion, it's a mixture of carbon dioxide, nitrogen, and water. And we want to separate the carbon dioxide so that you can basically put it through a chemical scrubber. And the main kind of chemicals that are used today are amine solutions. This is a very well-developed technology. There are newer technologies using chilled ammonia as an alternative. And basically what happens is the CO2 dissolves into this solvent. And then you take the solvent and you remove it from this contactor tower, and that you then strip the CO2 from the solvent, okay? And then that's done by adding steam, primarily done by adding steam. So you heat up the solvent, and then you have your pure stream of CO2, and then what comes out of here is just nitrogen and water.
Does it make any difference from a cost standpoint whether the input is natural gas or coal? Or is it essentially the same thing?
It does. Because from a natural gas plant, you might have about 5% CO2. So you've got now a really big, the ratio of nitrogen to CO2 is very big, so your contactor has to be bigger. The less CO2 you have in the gas stream you're trying to separate, the more costly it is. So there are people actually trying to capture CO2 from air now, 380 parts per million, 390. That's really expensive. So yes, so on the basis of per volume of air, it's less expensive to do it from coal.
What's that ZEF stand for? Is the company?
That's a European research program called the Zero Emissions Program. Yeah.
After you extract the CO2, is the solvent fully reusable?
Yes, fully is probably a little bit of an, that's the goal, is to completely regenerate. So the solvent is just used over and over again. But if you have impurities in the gas, it can basically contaminate the solvent. So you do need to do some makeup work and yeah. So the cleaner the gas that you're putting in, the longer your solvent will last.
Question. Is fractional distillation too expensive? Because as I understand, CO2 would be heavier than nitrogen. If you chill it and cool it in liquid, then CO2 will
Right. So ExxonMobil has a technology called controlled freeze zone technology that basically is cryogenic separation. But if you, depending upon how you do it, the CO2 can actually form a solid, which is a big problem. So they have a technology that first freezes it and then heats it up just enough so you can do the separation. So yes, that's possible. They have not been using it on like a power plant effluent, though I think that they're interested in checking that out. And GE actually has a new process, also a cryogenic process that they're working on developing. Yes?
What did you say the percentage of the CO2 was from a coal plant versus a...
It's about 14% to about 5%. Yeah, so 14 for coal, 5 for gas, yeah.
What are the implications of this scrubbing technique on other pollutant streams that are coming from, say, coal plants like organoleds and mercury?
Yeah. So basically, that if you're using this technology, you want your gas to be extremely clean, or you're having to spend a lot of money to buy new solvent. So you have to go through a sulfur scrubber. You have to go through a particulate removal. So there have actually been formal studies of the comparison of the effluent gas from post-combustion compared to high quality gas cleanup, and it's better. So basically, you get not only the benefits of removing CO2, but you're emitting a cleaner stream of gas. And I can get you those numbers.
You do still need upstream.
You do.
High quality scrub.
Absolutely. So this represents basically the last in your scrub. Now, if you were doing this with natural gas, it requires less cleanup. Okay, so this is one technology. So actually, here's just a picture of this. This is actually a plant in China done by the Huaneng Group, which is the largest electricity provider in China. And this is a little pilot plant outside of Beijing. And this has been operating for several years now. And basically, what these look like, you have these big contactor towers. So the first contact, so you've got water dripping down, or solvent dripping down, the gas going up. And then you take that solvent into a different tower, and then you basically run steam through it, and that separates the CO2. So anyway, I just thought a picture of what does one of these things actually look like. Okay, so that's the first technology. The second technology is something called oxycombustion. And the idea here is that instead of burning your fossil fuel in air, which is, 80% nitrogen nominally and 20% oxygen, why not just get rid of the nitrogen in the first place? So when you burn your fossil fuel now, you've just got your hydrocarbon, you've got oxygen, and basically you make carbon dioxide and water, and then whatever trace contaminants are there. And so here's a picture of this. So you have your air separation unit, you have oxygen and fuel going into the boiler, and then and your stream comes out as carbon dioxide and water, and it's easy to separate carbon dioxide and water. So this is an alternative technology to do the same thing. And then the final one is the most complicated of all. It's called pre-combustion capture, sometimes called gasification, sometimes called IGCC, or integrated gasification combined cycle technology. And the idea here is that, again, you have an air separation unit. You separate the nitrogen. Now you have a mix of oxygen and fuel. It goes into a gasifier, and it partially combusts the hydrocarbon. And what comes out of here is carbon monoxide, and hydrogen, and water. You then put it into another reactor where you react the carbon monoxide, and you ultimately end up with a mixture of carbon dioxide and hydrogen. And so basically the hydrogen is now your fuel. And if you have the right kind of turbine, which is not a routinely available turbine, you can then generate electricity with the hydrogen. And now you have your CO2 that you've just got to separate from the hydrogen. So that's basically how that works. Some of the advantages are, since you're producing hydrogen, you could actually use this for transportation sector as well. You could have hydrogen fuel cell vehicles. Yeah, so that's the big advantage. Now, one of the things that might be a little bit interesting to you, so I've been watching the capture community over the past 12 years or so. And when I first got in the field, everyone was sure that we were going to do IGCC, or we were going to use this technology, that the incremental cost for capture was comparatively small, and that it was a more modern and efficient technology. The overall efficiency of the plant could be greater. So when the comparisons between this technology and post-combustion capture began to be made, then the people who were promoting post-combustion technology said, well, I can make my process more efficient if I have a higher degree of integration, basically reuse of heat. And so then they showed their efficiency numbers were pretty good. And then they also argued that it was much easier to run. So if you use post-combustion, you basically run your power plant just like you run it today. And this capture unit is a sort of a standalone unit. And so that if your capture unit isn't working, you could always bypass that and continue to generate electricity. So they said it would be more reliable. And oxy-fuel, or oxy-combustion, was viewed as something really long off in the future. And what's really happened is that, at least from some people in the utility industry sector, they've gotten much more interested in this oxygen combustion, primarily because it seems sort of simpler. You know, right at your plant gate, you can have somebody who's generating oxygen, Praxair, Air Products. They basically ship oxygen to your power plant, and then the separation process for the power plant operator is very simple. So it's really, really fluid. I think that's the main point I want to make. Yeah, question?
It seems like maybe you couldn't retrofit oxy-combustion because of the pressure differential with nitrogen. You would have leaking into the system, is that?
If you did a simple, the view is primarily if you want to go to oxy-fuel, you really have to do a repowering. I mean, you can't just do a simple replacement. That there would be a significant capital investment. Yeah. So interestingly, we heard from Undersecretary Christina Johnson that FutureGen 2.0 has been announced. That was initially going to be an IGCC plant. Now they plan to have it be an oxy-combustion facility. So it's very interesting. And I think the reality is that we won't know which of these technologies ends up being the preferred technology. So now I want to show this chart, and I think this answers quite a few of the questions. I think most of the capture questions will get answered on this one. So here's the technology, and then advantages and challenges. So post-combustion capture, basically this is a mature technology. It's used for gas cleanup, natural gas cleanup, all over the world, and very well known. The chemicals are well developed, optimized, and so forth. And the second advantage is it's a pretty standard retrofit. What you mostly, if you want to do this, what you essentially need is a large piece of land where you can put this very large capture facility. Now, if you want to have a more efficient process, you need to work on process integration and so forth, but that's not a necessity. So that's the advantage, and people promoting this say, hey, this is ready today. So when you hear people say we can do capture and storage today, they're mostly thinking this in the back of their mind because this is the technology that's available. However, there are some real downsides to using this kind of technology. And in particular, it takes a lot of energy. I think one of the questions is how much energy does it take? And if you use post-combustion capture, 30% of the energy from your plant might go into the capture itself. So basically, you would really drop the efficiency of your plant. And of course, that wouldn't be desirable. And the other thing is these things cost a lot. And there are many, many assessments of the cost of capture. And I've given you some references in the back of the booklet that I gave you. And they range anywhere from, say, $30 per ton of CO2 up to several $100s per ton of CO2. And the range is not so much technology uncertainty, but what you've assumed as your baseline and so forth. Yeah, question?
So I don't have a good sense for $30 per ton of CO2. How does that correspond to a levelized cost of electricity?
Yeah, the simple way, it's 50 to 100% more in terms of cost of electricity. So anywhere from, say, 8 to 10 cents per kilowatt hour is a reasonable number with capture and storage for an nth plant, meaning a mature technology that there are, a suite of suppliers for and all of that. One of the things they're finding is all the first plants, because everything is custom, the one first of a kind, that they're coming in quite a bit higher than that. And if you are up at 150% of the cost of electricity, I wouldn't be surprised at all. Yeah.
And that includes the 30% extra energy that you have to
Right. Yeah, that's the whole thing. Yeah. Okay, so that's the technology, straightforward to use today. So what about some of these other technologies? So pre-combustion capture, the incremental cost to capture the CO2 is after you've built this IGCC plant is not so great, because what you're trying to separate out is basically more concentrated CO2, and it's an easier separation problem. However, building one of the, and so these plants are, if you want to put in maybe a 500 megawatt plant, you're talking about several $1 billion to build a power plant with capture and storage. So tremendously large investments. There's a project that GE is basically supplying the gasifier with Duke Energy in Edwardsport. So there will be a new IGCC plant going in. Another advantage is the amount of energy that you take away from the process is lower than post-combustion capture, so about a 10 to 15% energy penalty or derating of your power plant. And also this advantage that you are producing hydrogen as well, so you basically have co-products that you could sell to other markets. So those are the good things. So the bad things, though, is that this is a chemical plant. It's not like a power plant. It's not a steam generator. So the utility industry looks at this and says, well, what about my work? We heard about workforce today. Where is the workforce that used to run this technology, and now I'm asking it to basically run a complex chemical process. Second, it's not possible to retrofit. You basically are starting from scratch. And again, these plants do appear to have a higher initial capital investment than the alternative route going with post-combustion capture.
Do these build on the prior Texaco and other processes that EPRI investigated a while ago?
Mm-hmm. Yes, the Texaco process is one of the main competing options. Yeah. Okay, and then finally, oxygen combustion. The good part about it is that it's a comparatively simple thing. Once you have your oxygen and your fuel, it's a simpler operation, and also the separation is basically water and CO2, so that's very desirable. The other thing is under these conditions, you could combust under much higher temperature conditions, which makes it overall more efficient. The challenge is that we don't necessarily have the materials. So right now, what is planned is that you take CO2 and water. So some of the effluent you actually run back through the oxygen combustion to keep the temperatures lower. So there's some materials issues, but there are some good promise there. So there are downsides to oxygen combustion too. It costs a lot of energy to separate oxygen from air. So there's no free lunch, so to speak. And second, it's not a simple retrofit. You have to repower the facility. Yes?
Is there any potential role for membrane technologies?
Yes, there's a lot of interest in membrane. We support work in membrane technologies at Wright in Japan. There's lots of interest in nanostructured, metal organic framework kind of membranes and so forth. So yes, there's lots of interest. I'm not familiar with anyone who's close to something to use for these applications where it's wet and dirty. Yes. Yes.
So you say there's higher generation efficiency, but it takes energy to do the oxygen separation. Where does that net out in terms of?
So if you combust at the kind of temperatures that we're traditionally used to, the energy penalty is very similar to post-combustion. Yeah, but it could be better if we had different materials for the boilers. Yeah.
Would you never get better than baseline?
No. I mean, I can't. I mean, it takes energy to separate that. I mean, you can't get away from that. And the minimum amount of energy that it takes to separate CO2 from the flue gas is in the range of about 3 to 5%. So that's the best you could ever do if you had a perfect industrial process. Okay. All right, so I'm not planning to say anything more about capture. Any capture questions? No? Okay, good. All right, we're going to move on then. Okay, so the next two steps are compression and pipeline transport. These are basically mature technologies. We know how to compress CO2. We know how to compress other gases. We can also pump them around. And pipeline transport of CO2, there are thousands, 2,000, maybe actually more than 3,000 miles of CO2 pipelines in the United States, primarily in western United States and western part of Texas. So this is something that's done routinely today, and I really don't think it's much of an issue. Yes?
Yeah, we're pumping around something that has value right now. And if we decide to pump CO2, it's a valueless liquid.
Right.
So would society pay for that?
Well, it's the question of what we're willing to pay to solve the climate problem.
Could society pay for that? And the volumes that we're dealing with?
So the scenario that I showed you, the renewable energy, the efficiency, that whole scenario, those kind of scenarios are estimated to cost on the order of several $1 trillion, so I say $1.5 to $2.5 trillion per year for that entire portfolio of efficiency improvements and so forth. So that's sort of a couple % of GDP. So it's our choice. Do we want to deal with that problem for a couple % of GDP or no? So that's sort of the simple, superficial answer. Certain countries, it's going to be much more challenging than other countries, because there are a lot of pressing demands, particularly in developing countries, to provide energy access, healthcare, education, and so forth. So. Okay, so now we're going to talk about geologic storage. Yes?
What's the, how much energy does it take to do the compression and the transport? What's your energy penalty there?
Right, it's a couple %. Yeah, so the big part is the capture. And the second biggest is compression, so it's sort of about 1/3, well, no, maybe 20% for compression and the rest for capture. Yeah.
Are you thinking that you're not going to have to build a lot of new pipeline?
Well, there's, that is a question of whether you could reuse some natural gas pipelines. That's been considered, but at least for now, people are really considering building new pipelines. Yeah.
Pressures are higher, aren't they?
Not necessarily of the big lines. So these are 100 bar kind of pipelines. Yeah. Now, nobody said this is easy. I mean, changing our energy system is not going to be easy. I think it's, and no part of it is easy. Building more transmission is not going to be easy. Putting in 10,000-acre solar farms is not going to be easy.
But you're thinking that if you include the cost of building the pipelines, that the energy cost for pipelines is still only 2 or 3%, or is that without the cost of building all of the new pipelines?
So when you look at a life cycle assessment that included making the steel, so from a complete life cycle perspective, there have been a number of studies which suggest that the total amount of emissions reductions would be anywhere from 65 to 85%. So under certain circumstances, if you had very inefficient capture and so forth, you wouldn't get much of a benefit. Under the best of cases, you could have 85%. When you consider life cycle, which would include manufacturing the steel and installing them and all of that. No. Okay, so moving on to storage. Okay, so we now have this pipeline that's full of carbon dioxide that has been compressed to sort of a water-like consistency. And so the question is where are we going to put it? And not all rocks are suitable for putting carbon dioxide into. So that's the number one thing to realize. The kind of rocks that we think that would safely and securely store carbon dioxide are the same kind of rocks that trap oil and gas. Okay? So gas has a density of about half that of carbon dioxide. Oil is very similar to carbon dioxide. So this sort of the same force that results, this buoyancy force that would cause CO2 to want to escape from the subsurface is very similar to oil and gas. And we know that oil and gas has been stored underground naturally for millions, tens of millions of years. Otherwise, we wouldn't have oil and gas reservoirs. So what we're trying to do is find those same kind of geologic situations for storing carbon dioxide. So the kind of rocks where you find oil and gas reservoirs are in something called sedimentary basins. Okay, so sedimentary basins are rock deposits that basically form when mountains erode. So, you've got the tall mountain range, you've got the rain running down over it, it dissolves part of the rock, and then it transports like little quartz grains, and it deposits them in a valley. Okay, so that's how you form a sedimentary basin. And the rocks that are in that there are two types of rocks. One is called a sandstone, and it just looks exactly what you think about. It's little grains of sand in a matrix that cements it together. And these kind of rocks, all these places where you see the light green color, these are places where there are sedimentary basins onshore. And all of the purple areas are those regions where you have sedimentary basins offshore. So a quick thing is when you look at this map is that what you see, not all places have the same, equal access to sedimentary basins. So if you look at India, for example, you don't see a lot there. North America has got a lot, Russia a lot, the Middle East a lot. So these are variably distributed, but there are many areas in the world that overlie sedimentary basins. So that's part of it. So if you look inside of a sedimentary basin, what do you find? This is something we call a cross-section of a sedimentary basin. And what these are composed of are basically at least two types of rocks, sometimes more. But in this particular example, this comes from the Central Valley of California. So this is a cross-section from basically like San Francisco over to Lake Tahoe. And if you drive along the road on top of this, you're driving over this thick sequence. It's about 18,000 feet thick. So a very thick sequence of sediments. And some of the rocks are sandstone, like that picture there, the yellow. And some of the rocks are this gray kind of rock, and these are something we call shale. So these are rocks that are very, very fine textured. So if you think about clay, or clay mud or something that you step on and you slip, well, when that accumulates, it makes a very dense textured rock. And basically the idea is that you would store the carbon dioxide in these yellow regions, and these gray regions, or this shale, basically provide the seal. And in fact, these are just the kind of locations we find oil and gas in. As a matter of fact, there are many large natural gas fields in Northern California right in this region here. So with the gas trapped in these yellow zones and these gray shale-like rocks forming what we call seals, or a confining system. So this is what we're looking for, is places where we have sedimentary basins that have sandstones for storing CO2 and shales that act as seals. Okay, so that's what we're looking for. So it's a little bit more complicated than that in any sedimentary basin, there can be a number of different types of formations that we could sequester the CO2 in. So we could have depleted oil or gas reservoirs. Yeah, question?
So geological formations, if you go where oil and gas have been produced, what about in carbonate formations? Is it obvious that it's not a good?
Carbonates are present in sedimentary basins, and yes, you can sequester CO2 in them. They tend to be somewhat more complex in that the porosity is not so uniformly distributed, and certainly there is sequestration taking place in carbonates in Canada. Also there's a small project in West Virginia that's storing in carbonates. But most of the work is focusing on sandstone kind of formations. Yes?
It looks like maybe there's a fault on this picture. And I was just wondering, is there a correlation maybe between geologic patterns of ideal sites and faults? And does that cause problems with potential earthquakes?
Right. So if you're in an area with active faulting, where there's current day, movement along the fault, you would never want to store CO2 there because it can move, and it will move, it is moving, and you could create leakage pathways. On the other hand, there are many faults that were active a long time in the past that are no longer active, and in fact, there are many oil and gas reservoirs that those faults actually provide a seal. So just the mere presence or not of a fault wouldn't qualify or disqualify a site. It really depends more on whether you have active faulting and the state of regional stresses, which could lead potentially to the earthquake occurrence. Yeah. Okay, anyway, so we could put CO2 into oil and gas reservoirs, and the advantage of that is that we already know there's a good seal there. If there wasn't a good seal there, the oil and gas wouldn't be there. So that's sort of a logical, obvious opportunity, believed to be the lowest risk of all the opportunities. So you can do that. Second thing is that, well, what's a depleted oil reservoir? I don't know. It depends on the price of oil. So when we first started working on this, it's like, well, who's got a depleted oil reservoir? Well, nobody raised their hands. So the more practical approach would be to combine CO2 sequestration with enhanced oil recovery. And it turns out that that's actually a really good way to enhance recovery of oil. It's not cheap, but in some places it can be effective. So you could combine simultaneous oil extraction with CO2 sequestration.
Can you do any kind of mass balance calculation on how many sort of units of potential CO2 you'll get out for a certain amount that you put in order to get that more out?
Right. Yeah, and there are lots of calculations like that.
Do they come out like you're getting more out than you put in, or the other way around?
It's highly controversial whether you can get. I mean, some people like there's a company. Oh gosh, what's their name? Anyway, they're doing Denbury, and they do pure CO2 injection combined with oil extraction, they claim that theirs is net CO2 negative, that they sequester and store more than even all the CO2 that would be emitted when you use the oil. Other people use a combination of CO2 and water injection, something called WAG, water alternating gas. In those cases, it's unlikely that it would be CO2 negative. And I guess I tend to think of it as, that it's probably, you've got more CO2 content in the oil than you're putting in there, sort of on average, unless you really are engineering it very carefully. Yeah. Okay, so then the next choice is to put it in deep saline formations. So these are basically the same kind of formations where you'd have oil or gas, but there's no oil or gas there. It's just filled with salty water. Yeah, so a lot of interest in that. And then the final one, we actually had a question about coal, to put CO2 into coal beds. And that's possible too. Coal beds tend to be, or the ones that are accessible are typically shallower. And we had a question about how much CO2 you could store in a coal bed. And in coal beds, the storage mechanism is different. You don't actually store it sort of as separate CO2. The CO2 actually becomes part of the rock itself. It absorbs onto the rock. And if you have good contact between the CO2 and the rock, you can actually store a lot of CO2 in coal, as much and maybe even more than you could store in a saline aquifer, for example, even if it's cold, even if it's shallow, because you're not really storing it in the gas phase. You're storing it adsorbed to the surface of the coal. So I hope that answers that question. Okay. So moving along, so now we want to inject CO2 underground, and what happens? Well, here's sort of a little simple cartoon of what happens. So we inject CO2 into the sandstone reservoir. We've got a nice seal here so it can't escape, and we'll talk a little bit more about that in a minute. CO2 is less dense than water under these conditions. The CO2 may be anywhere from half to about 2/3 the density of water. So what does that mean? It means the CO2 is buoyant, so it's going to rise and basically fill this structure, and the water will be displaced laterally and downwards. So that's basically what happens. We need to inject deep enough for CO2 to be in a dense state. If we inject CO2 shallow, we're injecting CO2 gas, and the density is much, much less. So the general rule of thumb is you want to inject at 1 kilometer or deeper. And under these conditions, CO2 is called a supercritical fluid. And basically, it's sort of a dense phase. It has about 700 kilograms per cubic meter density, but it still has sort of got some gas-like properties as well, as the viscosity is quite low and the compressibility is quite high. So we want to inject it deep, and we need to trap it beneath this seal. So that's basically what we expect to happen. So one of the things I like to show is this picture. So in my lab, we do, question?
When it is in a gas state, does that mean it won't be sequestered underground and you won't be able to account for it, or what are the risks associated?
Right, so what it means is, one thing is when it's in a gaseous state, the density is very low, so you cannot store very much mass of CO2 per unit volume of the rock. So that's one issue. The second one is because it's less dense, the buoyancy forces are stronger. So if you were worried about it escaping, the risk of escaping would be higher. Though there might eventually be somebody who decides to store CO2 in gaseous form, but it's just generally believed to be more efficient to store it in a CO2 in a supercritical form. Yeah. So anyway, so in my lab, what we like to do is we like to look at rocks, and we take X-rays of rocks, we do CAT scanning of rocks, and we can look inside them, and we can see where the CO2 is and where the water is. So this is actually a picture of a real rock, and this is something called a micro CT image. So this is done at the Advanced Light Source at Lawrence Berkeley Lab, and we can actually look inside a rock. So here, the red are the mineral grains, okay? And one thing important to note, this is 2 millimeters across here, okay? So this is really tiny. This whole thing is, that big. And so we can see these rock grains are quite small. And the green here is water. So when we put CO2 into a rock, the water doesn't completely go away. So we have some water, and the black are these very, very tiny, tiny little bubbles. So one of the things when we talk about sequestration, I think people picture underground caverns or caves or whatever. But in reality, the CO2 is actually trapped in very, very tiny pore spaces of the rocks. Okay, so I'm just going to quickly, so there was, how it stays underground. So the primary reason it stays underground is because we have this seal present that has very low permeability and also has another mechanism called a capillary entry pressure. And if you don't exceed this entry pressure, basically the CO2 cannot push into the seal. So that's how it stays trapped underground. Okay, we've talked about costs. We said a little bit about earthquakes. We'll kind of come back to that. Okay, anyway, I think we're moving along the list. Okay, so what about safety and retention? And the problem is, if you've done something for a really long time, you can give a good examples. You can point to real-world experience. But we haven't done a lot of CO2 sequestration underground. And the IPCC did a big study in 2005, like they do all of their studies, to try to do a comprehensive assessment of the literature to evaluate the state of CCS, including storage. And there were a group of about 30 scientists who worked together for 2.5 years to study this issue. And they came up with two conclusions that were important. They were overarching statements. And the first is that one could anticipate sort of retention of on the order of 99% over 100 years or even 1,000 years and longer if you pick a good site, you inject CO2 under the ground properly, and that you monitor it to make sure nothing goes wrong. So basically that statement, which was carefully crafted like all IPCC statements, said basically if you find the right site, the CO2 storage should be essentially permanent. So that was important. Then the second conclusion was, again, if you do the project right, if you select the right site and so forth, that the health, safety, and environmental risks of CO2 storage would not be very different than oil and gas exploration and recovery, natural gas storage, CO2 enhanced oil recovery. So basically said, well, we haven't done CCS itself, but we've done lots of things that are very much like CCS. So that was one of the questions. Have we ever done anything like this before? In fact, we've done a lot like this before. And in particular, the best analogy is probably natural gas storage. That, as a matter of fact, McDonald Island, which if you drive through the Delta, you're driving across an enormous natural gas storage facility operated by PG&E that basically provides the natural gas for the city of San Francisco. And there are hundreds of these projects, about 460 natural gas storage projects in the United States and an equal number in Europe. So anyway, I think we had a question back there.
When you talk about these ideal sites, about how many of them are there in the world, and are they located close to population centers?
Yeah, about... So the way we've looked at this is we've looked at the location of all the point sources, and about 2/3 of the point sources are within reasonable proximity of a sedimentary basin. And reasonable proximity was sort of defined as 200 kilometers or so. Yeah, so many, not all, but certainly many of them are in reasonable proximity to a place where you could sequester CO2. Now, the question, you use the word, well, we're at population centers. I don't think anybody's really talking about sequestering CO2 under New York City or Beijing or London. These are things you'd probably do in a more remote area, just like the kind of places we do natural gas storage and so forth. Yeah?
So I looked at the map in the sedimentary basin and saw that China or India did not have significant storage options because they do not have any sedimentary basin. But they would use much of the carbon-intensive technology in 20 or 30 years.
Right.
So that seems to be a problem. It seems to me.
Right. So India, that is probably true. So India, much of it is overlays a type of rock called basalt, and And so that's one of the reasons we're doing, the research project we're doing is to look at could you sequester CO2 in basaltic rocks where the primary sequestration mechanism is formation of carbonate minerals. China, I think, is somewhat of a different question. When we first did this report, the IPCC report, the Chinese basically said there's no data on China. And other people said, oh, well, you know, the USGS has data, and the Chinese said, well, that's not our data. So in the meantime, there has been some other assessments that estimate that there's anywhere, I don't know, from 2,000 to about 3,000 billion tons worth of CO2 storage capacity. So, yeah, I mean, you know, time will tell on that. I mean, those are, you know, numbers done with kind of assessments that, you know, basically paper assessments. Okay, so those were, you know, yes.
During major heavy roadway construction or building construction, that sort of scenario, is there any potential for using it?
So there is interest in using CO2 to make carbonate minerals that could be used for aggregate, for example, for cement, for road beds and so forth. A company named Calera is investing in that. There have been lots of studies looking at mineralization using more traditional technologies, and they appear to be very, very energy intensive, and very, very costly. So, you know, I'm not so familiar with the details of the Calera process, so I really couldn't comment. I hope they've got something better, but the traditional mineralization approaches for doing it on the surface are very, very costly. Yeah, well, if you want to do it underground, natural, you know, then you have more time, and it could be, you know, that's one of the things we're doing research on. Yeah.
Has anybody suggested improving the economics by allowing other wastes in these super safe locations?
Right. Yeah. You know, that's a good question. So, you know, can you sort of put in other wastes? That's an open question now. In the European Union, they basically decided that they have some terminology like practically pure, you know, meaning you can't put these other things in, though they didn't find what, you know, 1% or 2%, something else. In the United States, I think it's less certain, but it depends on your solvent. If you're using post-combustion capture, you have to clean it up anyway. So you're not going to co-sequester those things.
I mean, you could put nuclear waste in there.
Oh, yeah, no, I think that's like, no. Yeah, I think the people who work on CO2 storage try to stay about as far away from that as possible because the level of hazards are just radically different. Yeah, so, yeah. Yeah, CO2 is, you know, it's hazardous at high concentrations, but it's everywhere around us. We breathe it in. It's, you know, essential for our life and so forth. So, yeah. We're not too comfortable with that comparison. Anyway, I just want to say, you know, those were very strong conclusions about safety and permanence. And so the question is, well, based on what? What set of arguments? Why should anyone be persuaded that this group of 30 experts has something to say about this? And basically, these are the reasons why the IPCC authors thought this. So number one, there are oil and gas reservoirs that prove you can store buoyant fluids underground. So, you know, so you've got a proof in nature that this is possible. Second, many oil and gas reservoirs also have CO2 in them. And so that it means that there's nothing particularly unique about CO2. It doesn't compromise the ability of the rocks to store CO2. There are also natural all-CO2 reservoirs that are present. So we have an analog in nature. So then the question is well, can humans do this? Can humans find good places to store CO2? Can we drill wells and not compromise the seals? So as I mentioned, there are many analogous activities, and we've been doing CO2 EOR. So this is you inject CO2 to enhance oil recovery for about 40 years. And today we're injecting about 40 million tons of CO2 underground for the purposes of EOR. So that's, let me see, what, so that would be like 5 gigawatt power plants equivalent CO2 is injected underground every year. So that's sizable. We also do natural gas storage, as I mentioned, the widespread practice all over the country. And in Canada, they do dispose of SO2 and hydrogen sulfide together with CO2, so-called acid gas injection on a very wide scale. Yes?
What's this technology, the state of the technology for monitoring and verification of how well the CO2 is?
I'm going to get there. Yeah, okay. So the other last important thing is there are some real CO2 storage projects in the world. The most important one is the Sleipner project offshore Norway. So it's off the coast of Norway, and it's sequestered in a saline aquifer. That's been going really well. There's lots of monitoring data from there, which I'll show you. There's a project in Canada at Weyburn. It's sequestration in an oil reservoir. Started in 2000. There's a project in Algeria, of all places, sequestering CO2 from a natural gas project. And then there's a new project in northern Norway. Yes?
Has there been a lot of studies on the natural CO2 reservoirs to understand why the CO2 stays in those particular reservoirs?
Yeah, not enough. There have been some, and they're published, and if you contact me, I can give you them. But there could be a lot more, and it would be very interesting. Yeah. Okay. So anyway, these are all the locations where gas storage is done. You can see broadly across the United States, all over Europe and the Soviet Union, former Soviet Union. So this is the project in Norway. So this is a gas production platform. The gas has too much CO2 in it to sell, so they have to strip off the CO2. They take that CO2 and inject it into an aquifer. And I'd like to show you the monitoring data. So this project was important, number one, because it was the first one and they did it. Second, because they were very public with the data. And in particular, they used something called seismic imaging. And you can think of it as a sonogram for the Earth to look for the CO2. So there are two different displays here. The one on the top here, so this shows a cross-section through the subsurface, and this is like a map view. So this was before any CO2 was injected, and you can only see two things, really. You can see the top of the storage formation and the bottom. And then about 7 years later, after they've been injecting for 5 years, they repeat that image, and lo and behold, they have tremendous differences. And all of these bright colors here are interpreted to be the location of the carbon dioxide. So importantly, you'll see the carbon dioxide is confined beneath the seal, and also it appears to be spreading out under thin layers of what turn out to be shale. So they've now repeated this several times. Actually, the most recent one was 2008. So it showed very nicely, you could see the CO2. It showed very nicely it's staying in the storage reservoir. And then these map views, you can show this growing plume of CO2. So this is about 2 kilometers wide and about 5 kilometers long. So this is the gold standard for monitoring where CO2 is going in the subsurface. Here's just a little bit more detail that sort of shows you the exquisite resolution. So we're looking at basically the very top of the reservoir here. And what I'll show you is images showing the development of the CO2 plume. So you can see that you can very precisely track where the CO2 is going. And I'm going to skip this. Okay. I'm going to skip this too. Okay, so I want to you had a lot of questions about sort of what could go wrong. I want to briefly talk about that. So I've given you sort of the basic ideas of how it works. But, it's always important to look at the downsides. I think that was, Pam Matson's, the main point is you want to look at the upsides and the downsides. So this is, these are the potential release pathways. So when you drill a well underground, it becomes probably the biggest source of vulnerability in itself. You know, you cement it underground, but as we all know from the Gulf Coast accident, that doesn't always work perfectly. So the wells themselves need to be very carefully constructed and monitored. If you characterized your site wrong, if you had an active fault and you thought that you had either no fault or an inactive fault, that could be a potential leakage pathway. Or also, you know, we heard questions about seismicity. If you inject CO2 underground, can you cause earthquakes? Well, what we do know is that if you inject fast enough and the pressure is high enough, you will certainly cause at least micro earthquakes. I mean, that's a very well-known phenomena. If you inject above a certain pressure, that you can activate movements along faults and so forth. However, there are laws today which govern the rate at which you can inject to keep the pressure below the level that would cause either cracking of the caprock or damage to otherwise damage to the seal. So, you know, yes, this is possible. But the question about microseismicity is one that I think we still have a lot to learn. Microseismicity can occur due to a couple of things. One is to the pressure buildup, but it also turns out if you have a large temperature difference, you can also generate microseismicity, which is something that is observed in geothermal areas. So I think as we go forward, we certainly want to do a lot of monitoring of microseismicity of these projects and learn how to operate them in such a way as to avoid that, because nobody wants to be shaking, having felt events and so forth. Okay, so these are the kind of things that can go wrong. Well, what are the consequences? Well, I think, you know, the number one thing at all projects is always going to be worker safety, that they are the most exposed individuals. So we can look to the oil and gas industry to look at accident rates and so forth there, and that's an excellent analog. Groundwater quality degradation. If CO2 escapes from the storage reservoir, groundwater degradation is certainly possible. Now, you know, we also get a joke, well, CO2 and water, well, what's that? That's Perrier, you know, we spend a lot of, or Pellegrino, if you like Pellegrino. You know, and that's certainly true, but it's, you know, if you have certain kinds of mineralogies where you have arsenic or lead in the rocks, which, you know, some basins do, you can mobilize that, and so somebody drinking that water may be exposed to unsafe levels. So the whole point is to avoid CO2 getting into the groundwater. When you inject it underground, it needs to be very deep where you're not using the groundwater. And in the United States, there are laws that says that it has to have higher than 10,000 parts per million total dissolved salts. So basically the plan, if a project goes to plan, the CO2 won't contact the groundwater. Resource damage. What happens if you're injecting CO2 into your gas field or something and it moves to your neighbor's gas field? They're not going to want that necessarily, so that needs to be thought about and managed. If CO2 does escape to the surface, it can cause ecosystem damage. Mammoth Mountain is a place where there are natural CO2 seeps, and there are large areas where the trees have died because CO2 naturally leaking out. You know, that's a natural geothermal system. So certainly if CO2 does come to the surface, you know, this is my list in order, I think, of highest risk to lowest risk. So way down the list is, you know, public safety. The biggest risk to the public is likely to be from pipelines, and, you know, something they have to be managed appropriately and carefully. But again, that's something we know a lot about how to do today. If you have some kind of land surface deformation, it's remotely possible that you could have structural damage. And then sort of last on my list is release to the atmosphere. You know, these projects executed properly are going to retain CO2 in the subsurface very, very efficiently. So this is really a very low risk based on all of the information we have about this technology today. So that's the kind of what goes wrong. And I'm just going to talk a little bit about capacity. the take-home message about capacity is think that if we decided to sequester CO2 in a big way, we could probably do it for at least 100 years before we would need to worry about running out of capacity. That's the sort of bottom line global number. Now, that doesn't mean every country is in that same situation. And the United States has done a big atlas of capacity estimation. So this is where oil and gas reservoirs are. About 60 years of storage in oil and gas reservoirs. Here's coal, about 80 years worth of capacity. Saline aquifers, so saline aquifers have the big capacity. In the US, it's estimated you could sequester over 1,000 years of CO2 emissions. So the United States actually has abundant sequestration resources. And so this is in your handout. This is the most current global compilation of the worldwide sequestration capacities. You can take a look at that. I'm just going to finish with it's time to go. Anyway, two things. There's a tremendous amount of interest in this technology around the world. Australia, China, Europe, North America, Japan are the primary points of interest. There are 238 projects on the books that are currently in one stage or another. It's my personal view that only some small fraction, maybe half or less, will really move along the development chain. But in the last couple of years, I have seen an enormous uptick in interest in this technology. I just came back from the Netherlands, and there were 1,800 people at a conference working on this technology. So industry is really, really very interested, and this map shows the location of those projects. I talked about cost. So this was just going to be my last thought to you about CCS. Like anything that requires land use, there are lots of regulatory issues, legal issues that need to be worked out, lots of issues of public acceptance. And CCS is still a technology that people are not very familiar with. And I think to be truthful, that the public is, on first blush, not terribly supportive of this idea. That it sounds very alien. The question, has anything like this ever been done before? Well, yes, we actually do a lot of this. So we're really going to have to do, if we're going to be able to implement this technology, if we as a society, as a global community decide to do this, it is going to take work making people more aware of the technology, developing the rules and regulations so people feel that their rights, their property rights are protected and so forth. And there are also some legal issues to do with the long-term liability. When CO2 is put underground, basically you're intending to leave it there forever. Our institutions don't last forever. And there's always the possibility that something could go wrong. I mean, you can never say nothing's going to go wrong. So developing a regime to deal with long-term liability issues is going to be very important before the industry jumps in to do this in a big way. And that doesn't mean the industry wants someone else to pay for it. I think that there's lots of discussion about creating trust funds or some kind of bonds to insure against future risks. But the institutional oversight and responsibility for maintaining awareness probably needs to be passed on to some kind of government overseeing body. And with that, it's time for us to end. And thank you for your attention and being awake still.
For more, please visit us at stanford.edu.